Hello, Geometry Honors, Section 3.2. We're going to look at using parallel lines and transversals and seeing some relationships that exist when you have parallel lines cut by a transversal. And the first thing we're going to look at is a postulate. Postulate 15, again, the number really doesn't matter. It just kind of lets you know how far we've come along. But postulate 15. Postulate 15 is the corresponding angles postulate. And we've been studying corresponding angles. We've looked at that when we had just two lines cut by a transversal, not necessarily parallel lines, but we realized where corresponding angles exist. And the corresponding angles postulate says if two parallel lines are cut by a transversal, then the corresponding angles are congruent. So a little picture of that is you got to have two parallel lines, and to show that they're parallel, you put an extra set of arrows on there. And then we want to cut it by a transversal. And say we've got angle 1 and 5. Well, do you agree that in this first picture we've got two parallel lines cut by a transversal? And do you agree that 1 and 5 are corresponding angles? Then what do we know from the corresponding angles postulate? We know that angle 1 is congruent to angle 5. And they visually look that way. They look like they'd be the same, and in fact they are. All right, let's use this a little bit. Example 1, identify the other angles that are 55 degrees. Explain your reasoning. Okay, and then it has a follow-up question as well. Well, let's see. You know, one thing that's jumping out at me right now, and some of you mentioned, or at least I know one or two people mentioned this yesterday in our notes, vertical angles. We've learned that vertical angles are congruent, the vertical angles congruence theorem. So I'm going to say that angle 2 is going to be congruent or the same as that, and yeah, it's the vertical angles congruency theorem. I should probably write that out, but I'm not going to. And then so we know that right there. Well, then because of that, we also know that corresponding angles are congruent from the corresponding angles postulate. So what angles correspond with this 55 degrees right here? Well, it would be this angle 4. So angle 4 is going to be 55 degrees. But also you could think of it as, what's the corresponding angle with angle 2? Well, that would be angle 7. So that's going to be 55 degrees. So we'll say angle 4 and angle 7 are also there, and we'll go ahead and do the corresponding angles postulate. And you know, maybe we should probably say vertical angles. Vertical angles congruent theorem. So yeah, we know all sorts of stuff just by using vertical angles and corresponding angles. They had a follow-up question there in the parentheses. It says, can you find the measure of the other 4 angles? What do you guys think? So the other 4 angles being 1 and 3, 5 and 6. Well, yeah, I think we sure could. And the reason I'm saying is we've got what kind of angle pair relationship right there. Aren't those a linear pair? So yeah, we could totally find that. I'm just gonna say yes, we could. And it's because we've got linear pairs all over the place. We've got linear pairs here, linear pairs here, linear pairs here, linear pairs there. We're gonna be able to figure out everything using that. So yeah, we've got some linear pairs. And so we know they're supplementary and we can figure things out. All right, so postulate 15 actually allows us to prove that a bunch of other angle relationships exist as well. So this is pretty fun. It kind of opens things up. So because of postulate 15, we can talk about theorem 3.1, which is actually the alternate interior angles theorem. And the alternate interior angles theorem says if two parallel lines are cut, guess what, by a transversal, then alternate interior angles are congruent. And we can draw a little picture of this. So we got to have parallel lines. How are we going to show they're parallel? Well, we add an extra set of arrows in the middle there. So those are parallel. Cut by a transversal. And let's say we've got, we'll call it angle 4 and 5. So if you've got parallel lines cut by a transversal and you've got these alternate interior angles, what do we know? Well, we know that angle 4 is congruent to angle 5. Alternate interior angles are congruent when you've got parallel lines cut by a transversal. Theorem 3.2 is pretty similar. It's the alternate, guess what, exterior angles theorem. And it says the same thing. Essentially, if two, and I'm sorry, it's a lot of writing, if two parallel lines are cut by a transversal, then what do we know? Then we know the alternate exterior angles are congruent. And a picture of this might be helpful. So we got some parallel lines again. Parallel lines, how are we going to show they're parallel? Add an extra set of arrows on there. Maybe you want to do doubles just for kicks, make it look ornate. And then cut by a transversal. And let's see, alternate exterior angles. So that would be like maybe angle 1. And I think if you counted them all around, that would be 8. Doesn't really matter. If you've got parallel lines cut by a transversal, alternate exterior angles are congruent. Angle 1 is congruent to angle 8. Now this last one is called the consecutive interior angles theorem. And it's the same thing. If two parallel lines are cut by a transversal, blah, 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 then consecutive interior angles are supplementary They're supplementary. Okay. Now let's look at a picture of this. Two parallel lines cut by a transversal. Oh, extra set. And let's go 3 and 5. So see how they're same side interior, consecutive interior angles. But take a look. See how this is an obtuse angle and this is an acute angle? They are not congruent. Is everybody with me on that? At least not in this picture. They could be in a special case, but they are not always congruent, and they certainly aren't in the picture I drew. But what is true about them is that angle 3 and angle 5 are supplementary. Now, what does that mean? They add up to 180, right? Now, if we were to prove this, I think we could prove this pretty quickly, and this is kind of a very informal proof, but essentially if this is angle 3, by corresponding angles, this would also be angle 3. And then do you see how angle 3, or angle 3's measure, I guess, it would be congruent to angle 3. And then do you see how these two together are a linear pair? What do linear pairs add up to? The linear pair postulate says they're supplementary. So there you go, boom. I think this makes sense. Okay, so let's flip this over and see what else we got going on. Oh, hey, you thought that you wouldn't have to do these for a little bit, but let's knock out a proof real quick. Let's prove theorem 3.1. And theorem 3.1, what was it again? We want to prove the alternate interior angles theorem. So let's prove it. Well, to prove it, we get to, since we've already established the corresponding angles postulate, I got a feeling we're going to use that to help us prove the alternate interior angles theorem, kind of like I used it to help explain consecutive interior angles theorem. So have that in mind. Let's see what we've got here. We've got a picture, which is nice, and we've got a given statement. Line A is parallel to line B, okay? And that is given, so our first step is already there. We've got parallel lines cut by a transversal. Our goal is to show that 3 is congruent to 4, okay? Well, I think I've got a plan here. I'm going to use the fact that 1 and 4 are corresponding angles to show that they're congruent. And I think what I'm going to do, oh yeah, and then I'm going to do vertical angles congruence theorem to show that 1 and 3 are congruent. And I'm going to write it in such a way that we can then wrap things up with the transitive property of congruence. So I think, let's see, I'll start with, I want to go from 3 to 4. So I'm going to go from 3 to 1 first. So I'm going to say angle 3 is congruent to angle 1. And how do we know that? Vertical angles congruency theorem. And then I want to link from 1 to 4. That way they link together. So I'm going to say angle 1 is congruent to angle 4. And how do I know that? Corresponding angles, yep. The corresponding angles, not theorem, but postulate. Accepted without proof. And then, do you see what I meant about kind of planning this out, linking it so everything matches there? 3 to 1, 1 to 4, so we can say angle 3 is congruent to angle 4 by the transitive property. Keep in mind, you might be thinking, well, you could just do substitution. Well, you could if you change these to measures of angle 3, measures of angle 1, measure of angle, but you'd have to take a step to do definition of congruence. It'd be some extra steps. But if you line things up, you can leave them as congruent and do the transitive property of congruence. There is no substitution property of congruence. So that's why I had to kind of think ahead to link things up. All right, let's use some of this stuff to do some algebra, shall we? Example 2 says find the value of x. Well, I noticed we've got some arrows here, so that means these are what kind of lines? Parallel lines cut by transversal. What relationship are they? They're corresponding angles, so we know that they are equal. And we can knock this out real quick, can't we? X is equal to 165. Moving right along. And I guess we could check our answers real quick. 165 minus 30. Yeah, we're good. Let's move on to example 3. Now, example 3 is a little more interesting. We have not 2 parallel lines, but 3 parallel lines. But what's interesting about them is each pair of parallel lines has a different transversal. Do you guys see that? So I think we kind of have to treat this in isolation of this. I think we're gonna have to look at them separately. Now, what's tricky about this is we have x and y's already mixed together, don't we? So I don't think there's gonna be a way to avoid it. I think we just gotta tackle this head on. We're gonna have x's and y's in our equation. And one equation I can write is we've got consecutive interior angles, and the consecutive interior angles theorem says that they are supplementary. So I'm going to say 3x minus 3y plus 60 is equal to 180. That's one equation I can write. Now, if I just had this one equation, it would be difficult to solve, to get actual answers for x and y. But we've got another equation we can write here. Now, here's what's interesting. This is kind of a special case. These are consecutive interior angles as well. And yes, they are supplementary. But think about this. If they're supplementary and this is 90, to add up to 180, isn't this one going to have to be 90? So you could totally write out 4x plus y plus 90 equals 180. But I'm just going to save a little bit of time, and I'm just going to go ahead and jump to the fact that 4x plus y has to be 90. Okay, so what we have here is we've got 2 variables and we've got 2 equations. This is a classic systems of equations problem. And you've learned to do these in Algebra 1 by either using, well, you could graph them and find out where the graphs intersect. That's kind of fun, but probably not the most efficient way. You could also solve these using substitution, or you could solve these by using linear combinations, otherwise known as elimination. So the way I'm seeing to do this is I'm probably going to do some substitution. And the reason I say that is I can easily get this y by itself. Now, why is that helpful? Well, if I've got y isolated, I can do the substitution property of equality, and anywhere where I see a y, I can replace it with negative 4x plus 90. And in fact, I'm going to do that right now. Now, why is this helpful? Well, first, let's be careful to put all this inside of y. Okay, why is that helpful? Well, it's helpful because now I no longer have 2 variables. I've got the same variables. I've got x's, so I'm going to be able to solve for x here. Let's clean this up a little bit. 3x, distribute, we'll get distributive property, right? We'll get 12x minus 270 plus 60 equals 180. I don't know. I guess I'll clean this up a little bit. Combine like terms, simplify. 15x, and this would be like minus 210 equals 180. And then addition property of equality, I'll get 15x equals 390. Divide by 15, and x is equal to 26. 26. So we found x, but we're supposed to solve for x and y. Well, the hard part's done, in a sense. Just take that x value and now do the substitution property of equality again right here. And now we'll be able to solve for y. Isn't that slick? Let's see, so that would be negative. Oh yeah, okay, so it'll be negative 14. Now this does make me nervous when I get a negative value, because in geometry we seldom have negative angles and negative measurements and things like that. But if you notice, we can check these pretty quickly. We can either check them in our equations here or kind of look up here and think about what the relationships are. But it turns out this y being negative is not a problem. And actually, if you take the time to double check these answers, you'll see that they work out just fine, just fine. So I use substitution here. Another way that you could do this is with elimination. And I would encourage you to talk with your neighbor and see if they recall what elimination is, and see if you can figure out how to set that up. I just don't really want to take time to do it in this video. This video is pretty long already. But another way to do this is with elimination. And yeah, if you're not sure what that is, Google it. Find out, do a little bit of research, see how to do that. It'll get you the same exact answers. It's just that instead of substituting initially, you basically work on eliminating one of the variables by adding or subtracting. All right, so the last example here says which angles are congruent, okay? Well, notice we've got some parallel lines. I mean, I guess they're actually segments, but I'm going to think of them as lines. And we actually have lots of transversals here. But I'm seeing that we only have one set of alternate interior angles right there. And that I can be really sure about. So I know that angle 2 is congruent to angle 4. But these other angles are kind of interesting. So angle 1 actually doesn't make an angle with one of our parallel lines, does it? So I don't think I can do much with that. Same thing with angle 5, okay? Additionally, you might be thinking there's a relationship between 3 and 6. But do you see how they're not on the same transversal? They don't touch the same transversal. So we're kind of stuck here the way they have the information presented to us. What you could do is realize that 5 plus 4, angle 5 and angle 4 together make an angle. 2 and 1 together make some angle. And then what you could do is you could say, well, we've got some consecutive interior angles. If we think of parallel lines cut by this transversal, we've got some consecutive interior angles. So angle 4 plus angle 5 plus angle 3 would have to equal 180, but that's not congruency. And similarly, you could talk about this big angle and this angle being supplementary as well. But the only thing that we can be for sure are congruent are angles 2 and angle 4 by the alternate interior angles theorem. And again, it's because they share a transversal and they touch. They are formed by the two parallel lines. All right, so there's some practice probably. I haven't actually looked that up, so let me look real quick and see roughly what your practice should be. Oh man, lots of good stuff, lots of good stuff. So I would look at page, you know what, I'll just stop here and I'll put it in the assignments in Canvas because I don't want you to have to do too many problems. All right, thanks so much for watching. Have a great day.